Hello everybody and welcome to my CST tutorial. In today's tutorial we'll be looking at stub matching within the schematic tool of CST. So first you want to open up a frequency domain environment, and I have a video on how to set that up in my beginner guide part 1. So once you've opened up a frequency domain simulation environment, you want to navigate over to schematic. So we're going to do the stub matching in the schematic tool, as we're able to tune the lengths of the stub and the position away from the load the stub may be. And we can do all this all in real time. So to start, you want to navigate over to the schematic tool, and we want to go to our block selection tree. It's down the bottom for me. You might not be able to see that, but you should be able to jump between the two pages of block parameter list and block selection tree. Once you've got this, we're going to go with ideal transmission lines to start off with. However, you can implement this with microstrip straight away. When I'm designing impedance matching circuits, I like to do everything in ideal transmission line. Then I like to transition into microstrip and then transition into a 3D environment. However, if it's a simple circuit like a quarter wavelength, maybe a stub matching you've already done on a Smith chart, it's quite easy just to implement straight away into 3D. However, the microstrip tool throughout the schematic tool is the easiest way to create a really novel impedance matching system, maybe over a certain bandwidth you would like. Okay, let's start. So the first thing we want to do is we want to create a 50 ohm port. So we're going to go up, we're going to click on our external port, and we're going to put port 1. Now the first thing we need to do is we need to force this port to be a 50 ohm port. So to do such, we're going to grab a transmission line, and we're going to go over into our parameters, and we're going to make a couple new parameters first. One being epsilon r, and we can make this any value we want. Let's just go 2.55. Remember, this is a transmission line engulf and the dielectric completely around the object. So if you were wanting to work in microstrip, you would need to put in this selection here the effective dielectric constant, or the effective relative permittivity. Okay, for the length, what we need to do here is we need to make it as small as possible so it doesn't impact the phase as much, but it still forces port 1 to be a 50 ohm port. Okay, and then we're going to put our epsilon value, and my variable is ER. Okay, what we're going to do is we're going to connect this up. Now here we have our 50 ohm port ready to go. So we're going to go back to our block selection tree, and we're going to click on circuit elements, and we're going to create our load. So here we have a resistor, so I'm going to drag that in, and I'm going to click R on the keyboard. So you put it on the side, and I'm going to go back to the block selection tree circuit elements and grab a capacitive element. Oh, there we go. And we're going to put it on the side. Okay, we're going to connect up our circuit. And we're going to interface the bottom point here with a ground. Okay. So perfect. Now we have a 50 ohm port looking into a load. So what we're going to do is we're going to tune the load to a mismatch, and then we're going to apply an impedance matching circuit. However, if someone gives you, like for example, a 7 ohm load, or they say an RC load of 1 picofarad and maybe 40 ohms, then you can input it straight away here. Or if they give you like a complex impedance, then you can scale that with the frequency. Okay, so I'm going to go over to resistance here, and I'm going to type the variable R, even though we haven't created it. I'm going to click enter, and a missing parameter will open up, and now we're going to define it. So I'm going to define it to start it off with 50. And I'm going to do the same for the capacitor. So capacitance, I'm going to change it to picofarad, and I'm going to make it C. and I'm going to set it to be, let's say 1 for now. Now we're going to go over into the top left hand corner and simulate what this load will look like. We're going to go over to Task, S parameter, click OK. Minimum frequency, let's make it 1, all the way up to 5. And if your computer can handle it, let's bump the samples up by a factor of 10. Make it 10,000 points, just to give us more accuracy and resolution over the Smith chart. I'm going to click OK and update. Okay, it should do it in about 1 second. I'm going to navigate over into the navigation tree and select S parameters. And it's easier to just go straight to the Smith chart. Okay, now we can see what our load looks like. So in the top left hand corner we have 1, meaning 1 gigahertz. And then the full color dot will be 5 gigahertz. So this is how the load changes over frequency. Okay. Now, what we can do is navigate over to Home and click this Tune button. Now we have control over the variables we have selected. So what I'm going to do is I'm going to leave the capacitance to be 1 picofarad. And I'm going to change the resistance from 5 all the way up to 50. So now as I change the slider, I'll actually change the real impedance of the load. And we can see how that impacts everything. Okay, so I'm going to say my load is perhaps, we'll make it a real load of 20. Okay, now we've got it over a frequency range. However, when we're creating impedance matching circuits, such as a stub or double stub, it's normally designed for 1 frequency. We're not designing a wideband impedance matching circuit. So what we're going to do is we're going to right click the working area and head over to plot properties. Deselect auto range and say you are asked to design it for 3 gigahertz. I'm going to put in 2.99 and I'm going to go 3.01. When I click OK, now I have a single dot to work with. Such as, let's say you're going on your Smith chart and you put a single dot on your Smith chart and now you want to do mechanically with a compass and a ruler stub matching. So normally you would flip it and then you would try and drive it with a distance away from the load to get this G equals 1. Get the point along here, and then you'd use a stub or a short to drive it back to this 1 point. However, when we're working in CST, there's another technique we use. The easiest way here is to first drive actually this point up to, if you click on Smith chart, top left hand corner, the drop down, we get the emittance Smith chart. We're actually going to drive it to the emittance G equals 1. So we're going to drive it all the way up to here or to here, and then we're going to use a stub or a short to actually drive it back down to the match condition. Okay, so how do we do that? Well, we're going to go first into our schematic, and we need to set up our transmission line length away from the load, because it's a single stub, and then our stub coming out. So how do we do this? Well, we can actually just copy and paste this transmission line element, delete the line in the middle, and plonk it in the middle. Connect it up. And with single stub, everything's still 50 ohms. So we're going to leave it as the impedance 50, and our length is the thing we're going to change here. So let's select a variable, D. And we're going to start it off with something very small. So practically, we haven't actually added anything in there. So let's now grab our stub element. So we're going to go back down to the block selection tree. We're going to go up to ideal transmission line and then grab the one that looks like an open stub, because that's easier to fabricate. In Microstrip, we don't need any vias. So the thing with stub elements is it likes to pull it down on the Smith chart, but we'll see that in a second. So now I need to update all my parameters. Epsilon R. The length, I'm going to make it L, and I'm going to make it something very short, so it's practically not there. And the impedance is the same. So if I go back to our old S parameters, here's the single point. I can go back to home and click update, start the simulation, and there we go, same spot. That's because we've set the lengths of the distance away from the load and the length of the stub, something very, very small, so it barely sees it. So now I'm going to click close tuner, and I'm going to go back to home, and then click tune one more time. Our parameters will now appear. So we have distance and we have the length here. So we're going to make the distance from this initial minimum value all the way up to, let's say, 30. And we're going to do the exact same to the length of the stub, 30. Now we're going to slowly tune our distance away from the load and see what happens to that point. Okay, we can see it transforming in a circle. So we know that if we have any length and it's 50 ohms away from the load, that you can put a compass in the middle of the Smith chart and just draw a circle, and you can transform it in a circle. So this point should zoot all the way around. So I've tuned it manually such that, so remember I'm on the emittance chart, such that the point is on this G=1 circle here. Okay, and the last thing to do now is to tune the capacitance value such that it pulls it down to the match condition. So we're going to tune the phase part of it. Okay, so let's go over to our length of the stub and slowly tune this value. Just a little bit at a time, and we see it coming down, a little bit too far. And let's say if we want to really tune the value, I know it's at 8.22. I'm going to do a minimum value of 8 and a maximum value of 9. Now I can fine tune it a little bit more. Okay, I'm going to zoom in. I'm quite happy with that. Okay, now that I've got the match condition, I'm going to right click, head over to plot properties, and I'm going to go auto range yet again. So there we go. We have our match condition at the frequency we want passing through the center. And let's now check our dB response. So perfect. Here's our match condition. So the next step is to take this and then implement it into a microstrip environment, which uses these blocks here. And now you can start using the same method and the same techniques with the substrate you would like. So for example, Rogers or FR4. And then once you've built it in this mode, you can then push into the 3D environment and then fine tune it. Okay, thank you for watching.